All right, chemistry, this is day 69, and we're still in the equilibrium unit, and this is on a concept called Rice tables, which is a way to figure out equilibrium concentrations and equilibrium constants. Okay, so the first page is simply a pre-assignment, so that's on the video starting at 1 minute, so we'll move on to the second page. Okay, so we're going to get started with our first problem in the assignment. So if the concentrations of SO2 and O2 are 0.1 molar, so here's the chemical equation up here, and the equilibrium concentration of SO3 is 0.075 molar, what is the value of Kc? Okay, so let's go ahead and write the law of mass action first. Okay, so convince yourself that that's correct based on this. Products on top, reactants on bottom, coefficients become the exponents. All right, let's start filling this out. So we're going to fill this in up here on the top. Okay, I like to draw the arrow to be sure that we separate which are the reactants and which are the products. Okay, so let's go through this. The initial concentrations, that's the initial line of these two are 0.01. So I'll go ahead and write that. I'm not going to write the trailing zeros. We'll just leave it like that and like this. Okay, and then it says the equilibrium concentration of SO3 is 0.075. So that means down here on the bottom for SO3. Be careful not to put it up there. That would be incorrect. So there you go. Now since they didn't give us an initial, we're going to assume it's 0. All right, now our change line is always going to involve the algebra, involve the x's. So it's going to be minus, and there's a 2 here, 2 and an x. So minus because it's reactant, it's decreasing in concentration. Okay, over here, same thing. It's minus. There's a 1 coefficient there, and then x. And over here, there's a 2, and now this is on the product side, so it's a plus 2x, like that. Okay, so it's almost like a little puzzle. What can you figure out? What can you fill in? Well, we started at 0 here, and we ended up at 0.075 here, so the change must have been positive 0.075. Again, this plus this equals the equilibrium. All right, I'm going to put this in parentheses here. So 2x represents 0.075. So what does x equal? It's just a little algebra problem. We'll come here and do that. 2x equals this. So now we're going to divide both sides by 2. Cancel. And we get x equals 0.0375. So that's the value of x. So if that's the value of x, then this negative 1x is going to have that value. I'm going to put this in parentheses. It's going to be negative 0.0375 because it's on the reactant side, so it's decreasing in value. So whatever this value is, 2x, 1x has to be half that value. And this 2x right here has got to be the same as this 2x over here. Only difference is it's a negative sign, so it's decreasing. Okay, so now you're ready to just do your additions or subtractions. So 0.1 minus this is going to be this. Okay, let's just do these on the calculator to be sure. Okay, so now we have our equilibrium values. That's the purpose of a Rice table, is to get either actual numbers here or to get algebraic expressions which you can then plug in. In order to make anything happen with algebraic expressions with x's in them, you'd need to know the Kc. But in this problem, we're trying to figure out the Kc, so we need actual numbers there. So now we're just going to go ahead and plug in down here. Okay, there you go. And now you just go ahead and calculate the answer for that. So 0.075 x squared, we're going to do that and get that number divided by, I like to just do these separate, 0.025 divided by 0.025 and then divided by 0.0625 and that gives us 144. So that's our final answer. Okay, no units of measure for an equilibrium constant. All right, we're going to move on. And, okay, an initial concentration, according to the equation, reacts according to the equation. At equilibrium, the pressure is 0.08. So what's the KP? It's exactly the same as the last problem. The way you compute KPs and KCs are the same. In this case, though, it's a gas, atmospheres instead of concentrations. Doesn't matter. It's the same thing, okay? So you're going to write the equation, and that one is initial concentration. It's going to go there, and it reacts. It says at equilibrium, the pressure of NH3 is that, okay? So it's a little bit different. So let's see. We're going to start with, and our arrow is right here, so we want to separate reactants and products. This is a decomposition reaction. There's a 1 coefficient there. I don't put the plus sign in, but I definitely put the arrow because I want to be sure I know which side is reactants, which is products. Okay, there you go. So it says initial concentration of this is 1. And it says at equilibrium, the concentration is 0.8. Okay, like that. So 1 minus what would give you, remember this is a reactant, so it's going to go down in value. So it's going to be minus 2x. Okay, because it's 2 and the change line always has an x. But we can actually figure out what the number is. 1 minus what number gives you 0.8, or you could say 1 minus 0.8 is what number? That's going to be 0.2. So what that means is negative 2x is equal to 0.2. So you divide both sides by 2, and you get x equals 0.1. Okay? And again, the negative sign is just because it's on the reactant side. So I'm going to say x equals 0.1. So over here you have some unknown, so you're going to say it's 0. But now you know that this is going to be a plus 1x. Why? Because there's a 1 there, and it's a product, so it's increasing in value. So it's plus 1x. And this one over here is going to be a plus 3x. So we know what x equals. It equals 0.1. So I'm going to put that in parentheses, just so we know we're not actually subtracting that. We're just going to subtract, or we're going to add this rather, 0.1. So that equals 0.1. Okay, and this is 3 times x. X is 0.1. So this is going to be 0 up here, and this is going to be 0 times 3x is 0.3. And that means we're going to end up 0.3 down here. So now you have all 3 of the values at equilibrium. You can write the law of mass action. So that's going to be Kp in this case. Okay, this goes on top. To the first. To the third. And down at the bottom is this. And that's squared. So now you just plug in your numbers, okay? You've got H2 is this number, N2 is this number, NH3 is this number. Do the math on that. Let me get on screen here. NH3 is this number, and do the math on that, and you'll come out with your answer for Kp. Okay, let's do another one here. Okay, this one's very much like the problem number 1. I'm going to leave that one to you to do. Might be almost exactly the same as problem number 1. So go ahead and do this one on your own. That's on page 4, number 3 on page 4. Come on over here. Okay, now we're going back in the other direction. We're given an equilibrium constant. It just says K equilibrium. These are probably gases, so it's probably a pressure, but we'll just call it equilibrium. It wants to know the equilibrium concentration of NH3. So it gives you equilibrium concentrations of these two, and then it wants to know the equilibrium concentration of this one over here. All right? So And it says create the rice table ourselves. So let's do that. RICE. You don't have to draw the lines. But we see we're going to have a reaction with 3 parts to it. So that's my double arrow. And over here is 3H2. Same equation we used before. Okay, now the next thing I really want to do is create the law of mass action here. So we're going to say it's a pressure because we know these are gases, even though it doesn't say that. Let's call it what it was called in the problem, K equilibrium. Just kind of generic name. Okay, so it's going to be... Okay, there it is. Convince yourself that that's the law of mass action for this. All right, now we're going to start filling in values. Equilibrium concentration of N2 and H2. So they're giving us these values down here. And that's going to be 0.5. I'm just leaving off trailing zeros here. And 0. Whoops, did that in the wrong place, right? 0.5 here. And 0.1 here. I'll go ahead and put the zeros. I don't want you to lose track of what numbers we're dealing with. I am going to draw a bottom line there. Okay, and this is actually what we're looking for. The equilibrium concentration of NH3, that number right there. All right? So we don't know anything about the NH3. We're trying to find this number down here, the equilibrium concentration. But we know the equilibrium constant, 3.81. We know the concentration equilibrium of N2, it's right there. And we know the equilibrium concentration of H2, it's right there. We really didn't have to do any of this. So now we're just going to plug in the numbers as we see them. So it's 3.81 for KEQ. And on the top we have this to the first power, this one. This one's to the third power. And down on the bottom, we have NH3 concentration squared, and that's what we're trying to find out. Okay, so it's really more of a math problem than anything else. So what I'm first going to do, just do it step by step if the math is a little confusing for you. So first of all, we're going to start off. I'm going to multiply both sides by NH3 squared. And that's going to cancel. Then on this side, I'm going to multiply it by NH3 squared. Okay, so we have that. Now what we're going to do is we're going to divide both sides by 3.81. We're trying to solve for this. We're trying to figure out what this is. So I'm going to divide both sides by 3.81. And over here, I can just put it down here somewhere. Okay, cancel and cancel. So then I have NH3 squared equals this times this to the third divided by 3.81. So I'm going to do that. First I do the exponent first, so 0.1 caret 3, that's 0.1 to the third equals 0.001. That's 0.001. Now I'm going to multiply that by 0.5. And that equals 0.0005, so all that's 0.0005. Now I'm going to divide by 3.81. And that gives us this 0.00013. So that's going to be NH3 squared equals, I'll go ahead and write it out as a decimal number, 0.013, and that's squared. So now we have to take the square root of both sides, and that will give us the concentration of NH3. So we're going to take this number, and now unfortunately you've got to just write it down. I'm going to clear it. So now we're going to do second x squared. That gives us a square root, 0.00013. close the parenthesis, and there's our answer, is 0.011. And that is a concentration, so it's molar. Okay, and that is our final answer. Okay, so let's read this. We have this reaction up here. It's a synthesis reaction, putting N2 and O2 together to produce 2 moles of NO. So you have 0.5 molar NO2 gas is mixed with 0.860 molar of O2 gas. So those are initial concentrations, initial molarities. What are the equilibrium concentrations of each substance? So they want to know everything down here. And we're given an equilibrium constant. Again, it could be a Kc or a Kp. It doesn't really matter. We're just calling it the equilibrium constant. Okay? So first thing, let's go ahead and write the reaction up here. And there's a 1 coefficient in both of these. And again, I like to draw the arrow so we know which is products and which is reactants. We don't make a mistake there. Like that. Okay, now we're going to write the law of mass action. Okay, there we go. Convince yourself that this is the law of mass action for that. All right, so now what we're going to do is we're starting with 0.5 MO2. Okay, again, I'm just leaving off the trailing zeros, and 0.86 of O2. And since we weren't given a concentration for our product NO, we're going to put it 0. So again, the change line, just remember, it always has an X. On the left side of the arrow, the reactants, it's going to be a negative sign. And then the coefficient in front of that is a 1. Same thing here, negative 1x. And over here, this is the product side. It's increasing in concentration, so that's positive. The coefficient is 2 and x. All right, so now the equilibrium is simply the initial minus the change here. And I'll drop the 1 in front of the x to put x. Over here, it's 0.86 minus x. And here it's 0 plus 2x. Okay, so there you go. So those are your algebraic expressions. And you do know a K equivalent value. Alright, so now we're going to plug in the K equivalent for our K equivalent there, and these algebraic expressions for each of these. Okay, so the 2x goes in here for NO, and then the 2 here, makes it a square. Alright, over here you have this. And 0.86. Okay, so be sure you understand. I'm off screen. Okay, so this was the N2. It goes right there. The coefficient, the exponent is 1, so there it is. Okay, and this one, 0.86 minus x, there it is. Okay, so now you use the simplifying assumption. You assume that x is much smaller than 0.5, and that x is much smaller than 0.86. And if you do that, you can just get rid of those x's. Just eliminate them. Because 0.5 minus a very, very tiny number will just be 0.5. And 0.86 minus a very, very tiny number, much tinier than 0.86, is going to be a 0.86. Okay? So now we're ready to do some math here. So I'm going to rewrite it, though, without those x's. Be sure you see what's going on here. And I'm going to also go ahead and simplify this. So 2 squared is 4, and x squared is x squared. So it's 4x squared over 0.5 without the x times 0.86 without the x. Okay, so that's what you're looking at there. All right, so now we're going to multiply. Let's do all this in one step. Okay, I think you're sophisticated enough. We're going to multiply the top of both sides by 0.5 and 0.86. So this cancels with this and this with this. So now we're going to do that over on this side. Anything you do to one side, you do to the other. Okay, and that's all going to be multiplied by this. And now we can divide both sides by 4. So I'm going to put a 4 down here. Draw that line a little further so it cancels. So that means we're going to divide this side by 4. Anything you do to one side, you do to the other. So now we've got our x squared all by itself here. That's what we want. So I'm going to put the x squared over on the left because that's usually the way you write a math equation. X squared equals, so I'm going to do 0.5 times 0.86 times 4.1 divided by 4. I'm going to leave the 10 to the minus 4th alone right now. Okay? I'm just going to put it in as 10 to the minus 4th. Or we could do the whole thing. Let's just do the whole thing. What the heck? We know how to use a calculator. So 0.5 times 0.86 times, and it's 4.1 times 10 caret negative 4. And I'm going to do an equals before I do the divided by sign. Let's just multiply all those. We get this divided by 4. And that gives us that number, which is, try to get it right side up here, it's 1, 2, 3, 4, 5. 4.4 times 10 to the negative 5th. That equals x. So now we take the square root of x squared, and we take the square root of 4.4 times 10 to the negative 5th. Okay, there we go. All right, so that means to get x, we're going to take the square root of this. So let's go ahead and do that. Let's practice that here. So second x squared gives me the square root. 4.4 times 10 caret negative 5, close the parentheses, and that gives us 0.0066. So we're going to call that 6.6 times 10 to the negative 3rd. Okay? All right, so that's our value of x. Now I'm going to draw a little space over here to do some further calculations so we don't get them all confused. Now, we want to know the concentration of N2 is going to be 0.5 minus x, 0.5 minus that number. Okay? So I'm going to do concentration. We wanted to know the equilibrium concentrations of everything. X is not that number. It's simply the number you plug into each of these down here on the equilibrium line to get the concentration. So the concentration of N2 equals 0.5 minus this down here that you can barely see, 6.6 times 10 to the negative 3rd. And that's going to equal, let's do that, 0.5 minus parenthesis, I like to put this 6.6 times 10 caret negative 3, close parenthesis, gives us 0.4934. We'll just call it 0.49. 0.49. So notice it didn't go down very much. It went from 0.5 down to 0.49. Not a big drop, but it is a little bit. Okay. All right. Let's straighten out a little bit here. Okay. Next is O2. So concentration of O2. It's this 0.86 minus our x value again, 6.6 parentheses times 10 to the negative 3rd. Okay, and I'm off screen. Let's get on screen there. There it is. 8.86 up above. I'll have to keep moving back and forth. 0.86 minus the x value, this right here. Okay, and what we get is 0.86 minus and that's 0.8534. We'll just call it 0.85. So it went from 0.86 down to 0.85. Okay, and that's molar. These are concentrations, so you have to put the molar. And finally, the last one is 2x. That's for NO. That's 2 times this number. Okay, and that's going to give us 0.0 it's a big enough number we don't have to use scientific notation this time. 0th molar, and that's for the NO. All right. Now we got to justify 5% rule. One last calculation. So our X value, is it less than 5% of our original concentrations? So we had a 0.5 and a 0.86. Okay, 0.5, it's much more likely to be greater than 5% of the smaller number than the bigger number. So we only need to do this calculation. Okay, so here we go. Times 100%. So let's go ahead and do that. So parentheses. And we get 1.32%. That's less than 5%. So the simplifying assumption, getting rid of these x's up here at this stage, was okay, because this is less than 5%. Okay? All right, that takes care of that problem. Okay, and number 6 here, the very last problem on page 7, is essentially the same as the last one. I do give you the answers here, so you can check those to see that you get it right, but be sure you know how to get those answers. And that takes care of this answers video.